Hello. I do want to cover a couple things that wasn't covered in the homework, but is still important. This, I think, is going to be covered later in the semester, but I do want to cover it now. So compositions, we talked about compositions a little bit before, but they are also related to this idea of an inverse. And two functions are inverses of each other if you take their composition in both directions and you end up with x. You end up with the original. And the idea of an inverse is that it is the undoing of one function. Remember, when you take compositions, one function is taking the range of the other function. Now, if you do that with inverses, you get x. But x was the original, that was the catalyst. That's the thing that started the chain reaction. X went into, in this example, went into G, which produced a y value. And then that y value went into F, which produced the original X. So F kind of undid the change that G did. And over here, G will undo the things that F does. It's really interesting to look at it in terms of ordered pairs. Here I've got this funky little function, a piecewise function. And I wrote down just several ordered pairs. -5, -2 is an ordered pair. -3, 0. I've got 0, -3, etc. To undo everything that the x produces is to essentially reverse the y's and the x's. So instead of -5, -2, I've got -2, -5. And instead of 1, -4, I've got -4, 1. So just the very fact of reversing the x's and the y's will produce an inverse relationship. And if it's a function, great. And it doesn't have to be, but it'll be, oftentimes it is. So let me show you a couple of examples. Like 1, that's a bad example. 2, in the green function, 2 produced 1. But in the inverse, if you give the inverse 1, it'll get you back to 2. 4 produces 5. So if you give it 5, it'll give you back to 4. Let me show you what this graph looks like. You could plot these ordered pairs, and what you get is it might be hard to visualize. I'm going to show both of them on the same page in just a second. But you get the green and the purple. So the green was the original, and if you switch all the x's and the y's, you would get this. Now, one consequence of this is that they are symmetrical about the line y equals x. So here you've got the green, the original, and the purple, the inverse, on the same coordinate plane. And then I graph the line y equals x. So it's very plain to see that it is completely symmetrical about that line y equals x. And the reason why it's y equals x is because, remember when we switched all the x's and the y's? Well, only when x and y are the same will no switching occur. So that's where the mirror happens. So how can we can also find the inverse algebraically without looking at the without graphically, but doing it algebraically. And it's all about forcing the inverse, which means just switching the x's and the y's, switching the inputs and the outputs, and then we'll solve for our new y. So here is a function, and I'm going to switch x and y. And now I've already got the inverse. This is the inverse. Now my task is to just solve for y. So how do I get y by itself? I always like to think y, you're adding 1, and then you're cubing that, and then you're multiplying that by 2, and then you're adding 9. So that's 4 things that's happening. So that means you have to undo 4 things. You have exactly 4 steps. And you start with the last thing that you did. The last thing we did was add 9. So I'm going to subtract 9. And then I'm going to divide by 2. Give me this. You may be tempted to distribute 2, but that's a massive mistake. You cannot distribute, you can't multiply before you do these exponents. So that would be, it's not even an option. And then now, how do you undo cubing something? There's only one thing that undoes cubing, and that is cube rooting. And then finally, subtract 1 on both sides, and you get this. This expression right here is the inverse of this function. And so the notation is y to the negative first power. Or if it were f of x, it would just be f to the negative first power. And if I were to graph this and graph the inverse, they would both be balanced out by that line y equals x. They would be symmetrical right there. Another thing I wanted to discuss is transformations very quickly. Transformations. So here we have this very fun function again. And I know you've seen this in Algebra 2 and pre-calc, but what does this do? X minus 2. It's inside the grouping symbols. It moves it to the right 2 units. You would have to go to the right 2 units to produce the same y value that this one would do. So all these x values just move to the right 2 units. Instead of -5, -2, this will become -3, -2. And instead of -3, 0, it will become -1, 0. And here's what it looks like. Literally every ordered pair moves over 2 units. What about 0.5 times f of x? Well, remember, this is the way you should think about it. F of x is y. So when you say 0.5 times f of x, you should think 0.5 times y, because they're the same thing. Well, if you take all the y values and you multiply them by 0.5, what's going to happen? It's going to shrink. Instead of being way up here at 5, it's going to be at 2.5. And instead of being at 1 right here as a y value, it's going to be at 0.5. And instead of being at -4, it's going to be at -2, half of it. What's interesting to note is that the zeros don't change. This y value of 0, if you take half of 0, you still have 0. So here's what that graph looks like. Notice it has the same zeros. It's just the height was just cut in half. Okay, let's finish up section 2.2. I want to just practice a little bit more with symmetry and being odd or even. So remember, so here's a function, y equals 3x minus 5, just a line. Can you tell me if it's symmetrical over the x-axis, the y-axis, the origin, or nothing? Well, to be symmetrical over the x-axis, which one did I do first? Yeah. If it's symmetrical over the x-axis, whatever's up here is going to go down here. And whatever's down here is going to be up here. In other words, all the y values, if you replace all the y values with its opposite, and if you get the same function, the same equation, it will be symmetrical over the x-axis. So I'm going to replace this y with -y, and you should be able to see right now that it's not the same, and it won't be. You could divide both sides by -1, getting -3x plus 5. Now it might be a little bit more clear, but they're not the same. So your conclusion is it is not symmetrical over the x-axis. Well, what about the y-axis? If it's symmetrical on the y-axis, then anything that was on the right is going to get flipped over to the left, and vice versa. So if you're talking about left and right, you're talking about x values. So if all the x's can be replaced with their opposites, and you still have the same function, then it's symmetrical over the y-axis. Well, take that x, replace it with the opposite of x, and I get, whoops, hold on a second. And you get y equals -3x minus 5, which is still close, but not the same. So it is not symmetrical over the y-axis. And there you have it, not symmetrical over the y-axis. Don't need to test the origin. The only way it's symmetrical over the origin if it's symmetrical both over the x and the y-axis. So as soon as it was over for the x-axis, the origin was not even a consideration anymore. How does this relate to odd and even? If it's even, It's symmetrical on the y-axis graphically. That's what an even function will look like. Here are 3 functions. They're all even. So in other words, if you took every single x value in these functions and replaced them with their opposite, you could not tell the difference. It would look just like that. I'm sorry, I keep on having to pause because my allergies are going crazy. But 3 functions here, they're all even. If to be odd means that if you replace both the x and the y with their opposites and you can't tell the difference, it's odd. Or in other words, another way to look at it is f of negative x, or f of the opposite of x, equals the opposite of the original. So the most common example is y equals x, the line is symmetrical about the origin. But y equals x cubed is a common example. Here's another cubic function just with some transformations. And you might think it has to go through the origin to be odd, but it doesn't have to be, because here's a piecewise function. These 2 red functions are a piecewise function, and they're odd. If you took every ordered pair anywhere in this red section and replaced it with their opposites, you couldn't tell the difference. It would still look like this. Relative max and min. The maximum and the minimum are y values. But the question, you have to be careful with the question, because the max and the min are the y, but it's also important to know, when does that happen? Where does that happen? And that's the x value. So we could say that the max and the min occurs at what x value? In other words, when does it occur? What x? And the max and the min is, what's the y value that it actually is? This graph on the left has no absolute maximum, what they call, because it goes up forever. It never maxes out, just keeps on going up, and it keeps on going down. So there's no absolute minimum. It has a bunch of interesting features that we should know. It has 3 zeros, negative 1.7, that's just a guess, 0, and then 1.7. It has a y-intercept of 0. It does have a relative maximum. So a relative maximum is a high point, a y value that is higher than other y values to the left and to the right. So this y value right here of 2 is a relative maximum, and that occurs when x is 1. And a y minimum is a y value that is less than the y values immediately to its left and right. And this y value is negative 2, and it is less than all the other y values are to its immediate left and right. So it's a relative minimum. The function does have y values smaller than negative 2, but not in the neighborhood of when x is negative 1. When x is negative 1, it's producing negative 2, and that's a relative minimum. This function is increasing between negative 1 and positive 1. It's decreasing everywhere else. So from negative infinity to negative 1, and it's also decreasing from 1 to infinity, or those intervals there. And then the domain and the range are all real. It goes to the left and right forever, and it goes up and down forever. This, again, no absolute maximum because it goes up forever. It doesn't go down forever, so it does have a minimum. It has a true minimum, an absolute minimum of negative 4. It'll never get less than negative 4. When does that happen? It occurs at around negative 1.5 as an x value. This has zeros as well, or x-intercepts even. So negative 3, 2, and 5 are the x-intercepts. It has a y-intercept of negative 2. It has one relative minimum. You could have multiple relative minimums and multiple relative maximums. The relative minimum is right here at it is negative 1, and it occurs when x is 4. And the relative maximum right here is 0. 0 is the greatest y value in this area, and that occurs when x is 2. This function is increasing in two different spots between negative 1.7, whatever that value is. Oh, I said 1.5 earlier. It'll be easier to change this. We'll just call this negative 1.7. So it's increasing from whatever where this minimum is all the way to this maximum. So from negative 1.7 all the way to 2. And then it's increasing again from 4 to infinity. It's decreasing from negative infinity to negative 1.7. And then from positive 2 to positive 4, it's decreasing. The domain is all real. It goes to the left and right forever. The range, however, begins at negative 4. That's the lowest range value, and it goes up forever. So the range is from negative 4 to infinity. And here's how the graph will be. It'll be displayed like this on the website, so it'll be easier to see and move around. One more quick idea, and then we're done. Something called the greatest integer function. You may not have seen this before. The greatest integer function is a function, and it's also called the step function, or some people call it the floor function. It's the weird looking one that just it looks like a stairway. And its definition trips people up sometimes. It's defined by the greatest integer less than or equal to x. Seems simple, but when you put it into practice, it might be a little slippery. Let's practice. The greatest integer less than or equal to the input. Well, what's f of 9.3? Well, I'm asking you, what's the greatest integer less than or equal to 9.3? And it's 9. 9 is the greatest integer less than or equal to 9.3. There are trillions and trillions of integers less than 9.3, but 9 is the greatest one. So it's unique. F of 5. What's the greatest integer less than or equal to 5? It's 5 itself, because it has that or equal to part. What about this? What is the greatest integer less than or equal to negative 14.6? If you said negative 14, you're wrong. You fall for it. It's negative 15. Negative 15 is the greatest integer less than or equal to negative 14.6. And just to show you the graphs, here's one example of a graph. It has 3 transformations. It went to the left. The order pairs got stretched. The graph got stretched horizontally, and then everything went up 1. But as you can see, it looks like a staircase, and all the inputs between 0 and 2 produce a range value of 2. All the inputs between 2 and 4 produce a range value of 3, and so on.